Hello everyone. In the continuation of our lecture series, today I am going to discuss the concept of lattice, which is one of the important type of partially ordered set. In the last class, we talked about some important terminology related to a hash diagram, which was maximal element, minimal, comparable, non-comparable, supremum, infimum. So if you didn't see that, go and see that first because in the concept of lattice, we do use the concept of comparable and non-comparable elements along with supremum and infimum. Okay, now let us start the today's discussion. Let me share the screen. Okay, so let us see what we mean by a lattice. So first thing, as we already know, what is a POSET? A POSET is a structure which is having a set along with a partially ordered relation, which is having a set along with a partially ordered relation. So if I am having a set A and it is having a relation R, and this relation is partially ordered relation. Partially ordered relation means what? It must be reflexive, it must be anti-symmetric, it must be transitive. Then this structure we called as a POSET. In short, POSET or partially ordered set. So a lattice is an extension of a POSET. A lattice is an extension of a POSET in which every pair of element is having both supremum as well as infimum. In simple word, a partially ordered set is called as a lattice if it is having supremum as well as infimum. That means whatever pair I can choose from your set A, it must have a least upper bound. It must have a least upper bound, or better to say, must have a unique least upper bound as well as a greatest lower bound. If this is the case, then that partially ordered set is called as a lattice. That partially ordered set is called as lattice. For a lattice, the notation in place of set, we use the letter L. A partially ordered set L comma R. L is a set, R is a relation where every subset A comma B of L has a least upper bound and the greatest lower bound. That means supremum as well as infimum. So how to prove a structure is lattice or not? So there are two things. The first thing is what? Prove the given structure is a partially ordered set by proving the given relation R is reflexive, antisymmetric, and transitive. The second thing is what? Now make a supremum as well as infimum table or composition table for supremum as well as infimum. And if every element of that table exists, we'll say that for every pair, supremum and infimum is exists, and the given structure is a lattice. Okay. If the question is asking prove the given POSET is a lattice, that means the question is already saying the given structure is a POSET. That means there is no need to check the relation satisfying the partially ordered condition or not. What we are supposed to check? Only do check it whether for every pair of elements supremum exists or infimum exists. If both exist, we'll say the given structure is a lattice. So this is what a quite simple and concise definition of lattice we are having. Let us take one example. So the first example is given as what? The set is given as 1, 3, 6, 9, 12, and the operation is divisibility. The easy part to get it supremum and infimum for every pair of element is what? Draw its hash diagram first. And from hash diagram, it's quite easy to understand that what are the upper bound, what are the lower bound, which one is least, which one is greatest, and easily you are able to decide that the supremum for every pair of element exists or not. Okay, as they have given us the given structure, we are supposed to check it. The first one is set this and operation divisibility. As we already proved, operation of divisibility is POSET. In the previous sessions, yes, divisibility is reflexive because every element divides itself. Divisibility is anti-symmetric because when A divides B, B divides A, then A and B must be the same element. Divisibility is also transitive because when A divides B, B divides C, then A must divide C also. The first part done, the given structure is a POSET. You can do it by yourself. I explained it. Now, moving to the second part, we are supposed to check in the second part that every pair of element is having supremum as well as infimum. For that, let us try to draw Hasse diagram of this. So this is your 1, then somewhere here 3, somewhere here 6, then 9, then 12. I already explained in one of the last session that how to draw the Hasse diagram. So operation is divisibility. 1 divides 3 years, then 3 divides 6 years. If I add 1 divides 6, it will be transitive as. So I will not draw it. Then 3 divide 9, yes. 6 divide 9, no, but 6 divide 12, yes. 3 divide 12, yes, but that comes out as a transitive edge. That comes out as a transitive edge. So this is what the hash diagram of this. It do not have any reflexive edge. It do not have any transitive edge. Can I say this structure is lattice? As the definition says, every pair of element is having supremum and infimum. So if I am finding the supremum, which is the least upper bound, if I am trying to find the least upper bound or the greatest lower bound, we can think on anything first. Suppose that I am trying to find the least upper bound, the least upper bound, the least upper bound, also called as a supremum of 9, comma 12. So first thing, we are supposed to write the upper bound of 9 and 12, the common upper bound of 9 and 12. Is there any element which is commonly connected on upper side of 9 and 12? No. So upper bound of 9 and 12, I can say not exist. Since upper bound of 9 and 12 not exist, so least upper bound is also not exist. As the definition of a lattice, it says that for every pair of element, it says that for every pair of element, least upper bound and greatest lower bound exist. Over here, I find one counter example which says that the least upper bound of 912 does not exist. Hence, I can say the given structure is not a lattice. That means in order to prove the given structure is not a lattice, it is sufficient to find a pair of element which is not having either supremum or infimum. It is sufficient to find out a single pair of element which do not have a supremum or do not have a infimum. So this is the first part, not a lattice. Let us take one more example. This time the operation is divisibility and the element is 1, 2, 3, 6, 12. As already proved, the operation divisibility is a partially ordered set in the first one. Now let us try to draw its Hasse diagram and then we'll try to find the supremum and infimum for every pair of elements. So this is what the position I decided. 1 divides 2, yes. 2 divides 6. 6 divides 12. 1 divides 3. 3 divides 6. 6 divides 12. Final hash diagram. Now there is no reflexive edge, no transitive edge. So this is the hash diagram. Now it looks like from this diagram that every pair is having supremum as well as infimum. But we have to verify it. Let us verify it. When you are you observe that the given structure is having supremum and infimum, then we are supposed to show it by using the composition table. Okay, so this is the table. Let us make the table of least upper bound or supremum. So how to make it on both the sides? Write all the elements 1, 2, 3, 6, 12, 1, 2, 3, 6, 12. Now the first element, what this first position says, the least upper bound of 1 and 1. What are the upper bound of 1? Every element is the upper bound of 1. 2 is the upper bound of 1, 3, 6, 12, and 1 itself. Upper bound of 1 is everything. The least one is what? Itself. Or as a result, we discussed that if we are talking about supremum or infimum for A comma A, it is always itself. Okay? So the least upper bound of 1 comma 1 is 1. The least upper bound of 1 comma 2. So what is the upper bound of 1 comma 2 first? Upper bound of 1 comma 2. Common upper bound. So 2, yes, 2 is the upper bound of 1 as well as 2. 6 is the upper bound of 2 and 1 both. 12 is the upper bound of 1 and 2 both. Can I say 3 is the upper bound of 1 and 2 both? No. 3 is the upper bound of 1, but 3 is not the upper bound of 2. We are supposed to write the common upper bound. So upper bound of 1 and 2 is 2, 6, 12, and we are supposed to choose the least one. So which one is least out of these 3? This is 12, this is 6, this is 2. The least one according to the relation is 2. So this is how the least upper bound of 1 and 2 is 2. In the same manner, the least upper bound of 1 and 3, the least upper bound for 1 and 3, if I listed upper bound of 1 comma 3, so what are the upper bound of 1 comma 3? Common upper bound is 6, 12, and 3. And the least one out of these 3 is 3. In the same manner, the least upper bound of 1 and 6. So what will be the upper bound of 1 and 6? 1 and 6. So 6 itself and 12 itself. 6 is the upper bound of 1. Yes, we can arrive from 1 to 6. Can I say 3 is the upper bound of 1 and 6? No. 3 is the upper bound of 1, but 3 is not the upper bound of 6. So 6 and 12 are the upper bound of 1 and 6. The least one is 6 as per the position in the relation. In the same manner, 1 and 12 is 12. This matrix is symmetric. This matrix, okay. So just calculate on the one side and the other side can be written it directly. Since it does not matter, I am finding the supremum of 1, 2 or 2, 1. That's why the given matrix is a symmetric matrix. Talking about second row, the least upper bound of 2 comma 1, it should be same as 1 comma 2. Least upper bound of 2 and 2 is 2 itself. Now the least upper bound of 2 and 3. So this is your 2, this is your 3. So if you are unable to write it directly, firstly list the common upper bound. So the common upper bound of 2 and 3 is only 6 and 12. Both of them can be moved to 6 here, 12 here. Common upper bound. Least one is 6. In the same manner, 2 and 6. In the same manner, 2 and 12. In the same manner, we can construct the complete table. So 3, 1 is same as 1, 3. 3, 2 is same as 2, 3. 3, 3 is 3. 3, 6. 3, 12. 6, 1 is same as 1, 6. 2, 6 is same as 6, 2. 3, 6 is same as 3, 6. 6, 3, 6, 6, 6 itself. 6 and 12 is 12. In the same manner, we can get this table, the least upper bound table. Now in this table, you can see it is listing all the ordered pair. These are the possible ordered pair out of 5 element, a 5 by 5 table. So we can say for every pair of element, least upper bound does exist. Now, can I say it is a lattice? The answer is no. Now I suppose to check it whether it is also having the greatest lower bound or not for every pair of element. So now we are going to make a table for supremum also. In the same manner as we did for infimum, now we are going to make a table for the greatest lower bound, or we can say infimum also. And if every element over there also exists, we call the given structure as lattice. Now let us make it as for greatest lower bound, GLB. In the same manner, make the table 1, 2, 3, 6, 12. 1, 2, 3, 6, 12. As already discussed, greatest lower bound or least upper bound for the same element is itself. Now I am talking for 1 and 2. So what are the lower bound of 1 and 2? See the hash diagram. Lower bound of 1 and 2 is common lower bound. It is what? Only 1. 1 is the lower bound of itself. 1 is the lower bound of 2. There is no other element which is common lower bound of 1 and 2, so only 1. So the greatest lower bound of 1 and 2 is 1. In the same manner, let us talk about this element which is 2, 3. So what are the lower bound of 2, 3? Just see the table. So the lower bound of 2, 3 is only one single element. The lower bound of 2, 3 is only 1. So we are supposed to check the greatest out of this one, which directly comes out as 1. If I'm talking about this element, which is what? The lower bound of 3 and 6. Now see, the lower bound of 3 and 6, the common lower bound. So 3, yes, 3 is the lower bound of itself as well as the lower bound of 6. 1 is the lower bound of 3 as well as the lower bound of 6. So 3, 6. 3, 6 is the lower bound of 3 and 6. Now, out of these two, we are supposed to write the, one, not 6, it should be 1. The lower bound we are writing, 6 can't be, because 6 is the lower bound of itself. 6 is the lower bound of itself, but 6 is not the lower bound of 3. So 1, 3, these are the lower bound of 3 and 6. Okay, out of these two, which is the greatest one? As per position, 3 is larger one. So this entry comes out as 3. So the table can be completed directly by seeing the hash diagram, or for any confusion, write the lower bound or upper bound for that pair, and out of that, find it out the greatest or least one and put it in the table. In this manner, you can complete this table. Now, every entry of this table will also be exist. The concluding remark, since the given set along with the given relation is POSET, the first condition satisfy. Also, for every pair of element in the set, supremum and infimum exist. Hence, we can say the given structure is a lattice. Hence, we can say the given structure is a lattice. So this is how we can check a structure is a lattice or not. So there are few more examples. I suggest you to try it by yourself. So these are the two more examples that we are having. The C part is for subset with the power set of A. Hash diagram for C part we done in the last session, I think. Then for this D part, D18 with the operation divisibility. D18 basically the collection of all positive divisor of 18. So what are the divisor of 18? 1, 2, 3, 6, then 9, then 18. These are the elements. These are the elements, and the operation is divisibility. Draw the hash diagram for it, and then check it whether for every pair of element supremum or infimum exists or not. If for every pair of elements supremum infimum exists, we will say the given structure is a lattice. Okay. So this is how in the today's session we talked about that what we mean by a lattice, how we can comes to know a given structure or partially ordered set is a lattice or not. Okay, I hope you understand this. Now, that's all for this session. Let us close this session.